Hi, I'm going to talk today about repeated sales with multiple strategic buyers. This is joint work of Nicole, Immorlica, Brendan Lucier, and Samuel Taggart. So first, this is an example we're all familiar with. We have a single seller and a single buyer. And the seller is trying to maximize revenue, and the buyer is trying to maximize their utility. In this case, we assume that the value of the buyer is drawn from a uniform zero-1 distribution. And the seller has to solve this problem. And the optimal price to place is equal to 1. But then I want you to think about another similar setting where there are now 2 days of selling the item. So the game goes as follows. We'll have a seller and a buyer. The seller is going, in the first day, the seller is going to offer the item at a price P1. Then the buyer is going to either accept or reject. Then the next day, the seller has an additional item to sell. And based on what the decision of the buyer in day 1 is, they will choose a price P2 of A, and then the buyer will either accept or reject. And in the case of reject, they may choose a different price, and again, the buyer will either accept or reject. So the buyer is interested in 1 item per round, and the seller can produces 1 item per round at 0 cost. So how will that game play out? Let's say, for example, that we use the optimal pricing scheme from the static setting. So the buyer is going to choose a price equal to 1/2. Then the buyer, assuming they are myopic, they would accept the item if the value is greater, if their value is greater than the price. Then the next day, the seller will update their prior over the buyer's valuation. Here, since they accepted the price of 1/2, it will be updated to uniform 1/2. And then they will offer a price of 1/2. And then again, the buyer will behave as a price taker. But in the case of reject, the distribution will be updated to uniform 0.5, where the optimal price is going to be 1/4. Now, if the buyer is myopic, that's a perfectly best response for the buyer. But if the buyer can look into the future and to decide how they're going to act, this is not optimal, because if their value is between 1/2 and 3/4, it's best for them to reject the first day, because they prefer getting the item once in the second day at a lower price versus getting it twice, first day and second day at the price of 1/2. So, and now you may wonder, how would an equilibrium look like in this setting? The answer is given by a previous paper by Emmanouil et al. It actually looks like this. The first price is equal to 0.3. The buyer is accepting only if their value is over 0.6, and this is actually important. So they're not acting like a price taker. And the last day actually behaves exactly as in the static model. So one other thing to notice here is that the total revenue that's generated is less than 1/2, which would have been if these 2 interactions were independent of each other. And in other words, if somehow the buyer had the option of committing to a price from the beginning, they would have made more revenue. And that's the central thing of the question we want to study here, is that we want to capture the lack of commitment through the notion of a perfect Bayesian equilibrium. We want to study the case of infinite horizon with discounting. And in this particular setting, we already know that the maximum revenue that the seller can generate in an equilibrium is no more than the milestone benchmark. What is the milestone benchmark? Running milestone every round. So the case where you can commit to a price. And the question that we would like to address is, are there perfect Bayesian equilibria that have a revenue that approximates, ideally being a constant fraction of that milestone benchmark? So let me go a little bit through the related work. There has been a lot of work, especially in economics, in this area. The paper Harden-Tirole discovered a no-learning equilibrium for this setting when there is finite horizon and the buyer can have 2 potential values, a low and a high. Smith extended these negative results for when the buyers can have multiple values but still being in a discrete valued setting. There's a nice survey by Vandenberg, Villas, and Boss. And one of the most related paper to ours is the Emmanouil et al., where they studied the finite and infinite horizon cases with continuous distribution, as we do in our paper. And they show that they show a negative result that there is no threshold equilibrium for finite horizon and more than 3 rounds, which will be formally defined later. And that there exists equilibria under some alteration of the model where the seller can partially commit can have a partial commitment power, and that approximates the Martian benchmark. So again, what are our main results? We show that for the single seller, single buyer, there exists a focal equilibrium where no information is revealed by the buyer that generates minimal revenue. This is an extension of the Hart and Tirol result for the case of continuous distributions. And we show that when there are at least 2 buyers, for each class of distributions, there exists an explore-exploit type of an equilibrium that approximates within a constant function the Martian benchmark for the single item in the digital good settings. Okay. So let's describe formally the model right now. We have one seller that produces a single item each day at no cost, or either a single item or a digital good. We have n buyers. Buyer I has value vi for receiving one item at each day, and this item is going to be remaining the same. It's going to be drawn in the beginning from distribution f, which is symmetric, and it's going to remain the same across all days. So think of it as the seller is trying through all of these interactions to learn that value v, so that they can earn more and more revenue. And we assume that both the seller and the buyer use a common discount factor delta. So and our solution concept is going to be a perfect Bayesian equilibrium. And for you, most of you should be familiar with the term, essentially, that beliefs should be updated as much as possible using Bayes' rule, and the seller and the buyer should be best responding to the other agents in the game for any possible history. And a particular refinement of equilibrium we're going to consider is this, what we call threshold equilibria. A threshold equilibrium is an equilibrium where the buyers are using a threshold strategy. What is a threshold strategy? It's a simple strategy where the buyer is going to, given any price p, they will accept the price p if their value exceeds a certain threshold that depends on that price. So it's not randomized, and it's monotone, I would say, in terms of value. What do we show for the case of a single buyer? First, we show something quite strange, that there exists a Folk theorem, right? So give me any price, there exists a threshold at PBE that actually posts that price for all rounds for continuous distributions. Essentially, this means that the Martian benchmark can be achieved. But this is using some extremely strange continuations. And once we refine them by using some Markovian assumption and some natural assumption, which I will refer to you to the full version of the paper for the description, then the only equilibrium that remains is the one where essentially the seller is giving it for free every round, which corresponds to the equilibrium of Hart and Tirol for the case of discrete valued agents. So what is the main reason for this result? So the main reason for why in a single buyer, single seller equilibrium, the seller can generate no revenue is essentially that revealing information is costly to the buyer, and the buyer's strategic response drives the revenue down. It's exactly the idea that there is asymmetric information, that only the buyer has the information about the type, and the seller is the one that, this is the asymmetry of information. So our idea is to introduce another buyer where essentially breaking that asymmetry of information now. The price of the item now depends on both buyers' actions, and therefore the buyers are slightly more incentivized. They don't care so much about revealing information, which manages to improve the revenue considerably. And for that, we define an equilibrium. We identify a perfect Bayesian equilibrium that has a nice and intuitive form of should all be familiar with it, which is an explore-exploit algorithm. So let me demonstrate how such an equilibrium would look like. So in the beginning, the seller is choosing a price P, and that price P has a threshold T of P for accepting. Now, we assume here that the values are drawn for buyer 1 is going to be V1, and for buyer 2 is going to be V2. So in the first round, the seller is posting price P, and then T of P is the threshold for accepting. Both people are above TP, so both accept. And now the seller is updating their priors. Now the beliefs over the buyer's value is that their support lies in this is that interval. Now the next day is going to post a new price P with that threshold here. Again, both people accept, and the sellers update their belief to this value, to this interval. And finally, the third day, we have the price P has a threshold that exceeds buyer 1's value. That means that buyer 1 rejects and buyer 2 accepts. This is going to change the beliefs like this. And we say that the exploration phase of our equilibrium stops here, and now the seller is going to exploit by just offering it to the person that has the highest minimum value of the support. So the way that this is going to continue, the seller is going to post always that price here, and the item is always going to be given to buyer 2. So, and the interesting thing is, what is the relationship between this is the only mathematical slide I will have in this presentation. It's going to be, what is the relationship between the price offered and the response? And actually, this relationship is given by this. So we're saying that a threshold type T of P, what does this equation say? It says that if you are the threshold type, the type that is indifferent between accepting and rejecting, it should be that the utility of accepting is equal to the utility of rejecting. So just to briefly interpret what the math here, this is the probability to get the item if you accept. This is today's utility of accepting. This is the probability that, so what happens is that the only way of us getting utility if we reject it is that the other person rejects as well, because if the other person accepts, then the seller is going to only post and give the item to the person that accepted, as we showed the previous example. So only in the case of reject, we may get some utility, and that's how much the utility is for the case of rejecting. So this essentially constrains, this dictates the relationship between P and T of P. And we can, given such a function T of P that is passing, that is satisfying the previous equation, we can define an equilibrium where it goes as follows. During the exploration phase, the bar is going to behave according to that threshold response, this T of P function. And during the exploitation phase, they will just accept if the price offered is the minimum value of the support. And in the exploration phase, the seller correspondingly will offer a price that is maximizing, that has a threshold response and that maximizes the expected revenue. And in the exploitation phase, they will just offer the minimum value of the support, highest if they are different. So what are our results with respect to this is that the previous equilibrium that I described forms a PBE, and that for a large number of distributions, this PBE actually guarantees a constant fraction of the Martian benchmark as revenue for the seller. And the real challenge for, eventually you can think of it as this explore-exploit equilibrium producing the efficient outcome, right? So this explore-exploit equilibrium will only stop the moment one person rejects. And the moment the person rejects, we will almost sell the item to the person that didn't reject at the second highest value. So essentially, it's implementing somehow VCG. So, and which we already know it's going to be good revenue in this case. But the real challenge is that showing that the discount factor hasn't been too low the moment that happens. So the real challenge for showing the revenue result is that the learning occurs at a fast pace. So as I said, what our equilibrium manages to implement in this case is the efficient outcome, which we know has good revenue in the terms of a single item. But when we go to digital goods, in which case, let's say there are two items, here, when we have two buyers. The efficient equilibrium, the efficient outcome, sorry, doesn't guarantee good revenue. Actually, the efficient outcome for digital goods has a revenue of 0. What happens here is it's something extremely interesting, is that if the seller is allowed to use discriminatory pricing, then we can essentially prove that this is the unique outcome. The unique equilibrium actually is going to be the efficient outcome, and the revenue generated is going to be trivial. However, if we are restricting the seller to use an anonymous price, that suddenly allows us to show the existence of a threshold equilibrium with non-trivial revenue. And again, the formal theorem statement is that if the seller is restricted to use anonymous pricing, there exists a threshold PBE where the seller obtains a constant approximation of the milestone benchmark for a large family of distributions. And to conclude, some future directions, questions is, what if the seller is able to use anonymous reserve auction instead of pricing? So, and then the question will be, instead of changing the price, we choose a reserve. So how would that interaction be? How would the PBE in this setting of a mechanism look like? What if this, a typical question that is asked in this case, what if the seller also has a private cost? And therefore, that's another way of breaking the asymmetry between the information. And what we would like to do is, can we formalize this connection between the revenue extraction and learning in equilibrium and privacy? Because here what happens is, once the buyer was the only person in the game, the consensus of privacy was so important. Consensus of privacy, like the reason why there was not enough revenue was that the buyer did not want to reveal that information. And once the second buyer was introduced, then their information was not that valuable. Therefore, they were willing to reveal it. So yeah, and with that, I would like to thank you.